Hello, welcome back to Astronomy. This video, we're going to go over 11.4, stars slowly become red giants. Hopefully you guys are kind of used to the online thing. I know Google Hangouts probably would have been a little strange to do by the time you're watching this video, though you're probably already used to it. Please make sure you guys, again, are reading the book on your own time, as well as listening to these videos, because not reading the book you're going to miss a lot of background information that you may not pick up the first time just listening to the PowerPoint. So let's go ahead and go through this. 11-4, stars slowly become red giants. Remember, we're looking at the life patterns of stars. Let's see, 11.1 was talking about how stars form. Remember, they form from the gravitational collapse of clouds of dust. And that can be from other stars or dust floating out there in nebulas and stuff like that. 11.2, we know that most stars shine through their lives by converting hydrogen into helium through nuclear fusion. So we looked at that a couple chapters ago with the proton-proton chain. That's how most stars shine throughout their lives. We know there was a couple examples, a couple of exceptions to that. we saw how the red dwarf, it does do that, but it gets to use up all of its hydrogen over a very long period of time, to where we haven't actually ever seen one of those burn out. And then we found out that we can look at star clusters and find out how a star's mass influences how stars change over time. Or we can also look at the spectrum of a star and see what kind of materials are inside of that. That's how we got the population 1 and population 2 stars, which means the population 1 stars are metal rich. They have metal in them, which means they probably formed from the dust of other stars. And population 2 stars, which are metal poor, which means they might be some of the first generation stars. And the very last note of 11.3 was a star's mass determines its main sequence lifetime. So we found out that the more mass a star has in the beginning, the quicker it will die, the faster its life cycle is. And that's kind of just like it burns through all of its stuff a lot faster because it's a lot bigger. So we're going to look at the fate of stars that are a little more massive than 0.4 solar masses. Anything smaller than that, remember, we don't really count those. We're just looking at the smaller kind of stars, 0.4 solar masses or larger, up till I think 2 or 3 solar masses, so 2 or 3 times the size of our sun. Well, we do know that the central core of a star is the location of the highest pressure and temperature, and it is where core fusion occurs, right? We've talked about that before. When a star of at least 0.4 solar masses reaches the end of its main sequence lifetime, though, all of the hydrogen in its core has been used up, and hydrogen fusion ceases there. So that's kind of strange, right? It's supposed to be forming in the middle like this note says, but it is possible that it can run out of fuel. And when it does, what can happen is that hydrogen fusion can continue, but only in the surrounding shell of the hydrogen-rich material outside the central core. So we have the core that was doing the fusion, but then the core hydrogen kind of runs out. But if it's hot enough, the shell of the core can actually start undergoing hydrogen fusion. Okay? So if the core runs out, if it's hot enough, the shell can actually start undergoing hydrogen fusion. And it typically goes, we say that a star enters the main sequence group once they begin hydrogen fusion, and they leave the main sequence once their core hydrogen is depleted. Not all of their hydrogen, but their core hydrogen. Okay? So go back to this. They join the main sequence when they begin hydrogen fusion, and they leave the main sequence when they're done fusing hydrogen in their core. Okay? They're still fusing hydrogen in their shell, they're just not fusing hydrogen in the core. So the end of hydrogen fusion in the core actually increases the core temperature. I know that sounds strange, because we just said, well, if it runs out of fuel, how's it going to raise the temperature if there's nothing happening down there? So strangely enough, the end of hydrogen fusion in the core increases the core's temperature. When thermonuclear reactions first cease in the core, nothing remains to generate heat there. Therefore, the core starts to cool and the pressure supporting the core starts to decrease. So what that means is that the pressure decrease allows the star's core to compress. Okay, so it's no longer making any heat, so the whole star can compress on the core. However, you guys know once you start squeezing something, you start heating it up. So in a weird backward thing, as the core starts to contract because it can't make any heat, its temperature starts to increase because it's getting squeezed. And because of that, the heat flows outward from the core, even though there's no fusion taking place. Okay, so it runs out of fuel, it starts to squeeze down, and because it's squeezing down, it starts to heat up, which again squeezes out. It's like this crazy cycle. During this post-main sequence phase, the star's outer layers expand just as dramatically as the core contracts. So remember, the core is being squished. And it's being squished so hard that the temperature can increase from 15 million Kelvin to about 100 Kelvin, which is pretty crazy. As the hydrogen fusing shell works its way outward, egged on by heat from the contracting core, the star's luminosity increases substantially. This increases the star's internal pressure and makes the star's outer layers expand to many times their original radius. That's what's on this picture right here. So the interior is being squished. Because of that, it's starting to release a bunch of heat. This actually, even though the core isn't undergoing any fusion, the shell is undergoing fusion. And because the shell is undergoing fusion, it heats everything else up on the outside, and then the outside expands. Once the temperature of a star's bloated surface falls, the gases glow red instead of the yellow or orange that we used to have. Based on its new appearance, the star is then appropriately known as a red giant. Thus, we see that red giant stars are former main sequence stars that have evolved into a new stage of existence. So the red giants that we've been talking about are actually just what happens after a main sequence star stops being a main sequence star. Okay? It runs out of the fuel for hydrogen fusion in the center, so it cools down and it squeezes down. However, once it starts squeezing down, it heats up the core, which allows fusion to happen on the edge of the core. Since the fusion is happening on the edge of the core, it makes everything expand. Since everything gets to expand out here, instead of being hot, it spreads out and cools down into red. Because remember, we talked about when stars are red, they are cooler. And here's a picture, almost a step-by-step. It's not really to scale, but almost a step-by-step of what's happening. So we have a main sequence star with the hydrogen fusion core, a young red giant star. The interior is helium, because as hydrogen fuses right here, it makes a bunch of helium. The helium is just stuck down there. That's why it says no thermonuclear reactions. But as we've been saying, the hydrogen can still fuse on the shell. Since it's fusing on the shell, it's expanding all of this gas out here. Okay? And we'll get to this picture in just a second. So then why does a red giant appear red if it's cool? Well, we know that the more red something is, the cooler it is when compared to like the color yellow or orange or blue. The more red it is, the temperature is decreasing. Okay, so going back to this picture, we got this part down, but it is possible that the helium can start to fuse. Okay, so we ran out of hydrogen for the hydrogen fusing core because it made so much helium. But now that we have hydrogen fusing out here, and remember this is now increasing the temperature, it's possible to increase the temperature on the inside so much that it's not hydrogen doing the fusing anymore, it's helium doing the fusion. Okay, so we switched fuel sources. We started with hydrogen making helium. And then we switch to here where helium can't do anything, but hydrogen is still making more helium on the outside. Once that happens a little too much, the interior gets so hot that helium can now fuse into heavier elements, and the hydrogen is fusing on the outside. Okay, and we learned the proton-proton chain was when the hydrogen atoms are combining to make helium. Now we have a new process. The triple alpha process is what combines helium atoms to form carbon atoms and releases energy. So this is like the next step. Okay, the proton-proton chain is how our star is kind of running right now, how a lot of stars run right now. This is after it's done doing that, after it ends the main sequence, when it's in its red giant phase, this is what's happening. Okay, so we see that the hydrogen fusing shell is still going on, and it heats up so much that the temperature and pressure become high enough for helium nuclei to start fusing together. So instead of two hydrogens, we have two heliums that squeeze together, and they make a beryllium atom. But this thing is not very stable. It doesn't last very long. You see it's 7 times 10 to the negative 17th seconds. That's how long it exists. Most of the time it just breaks apart. However, if in that extremely short amount of time it happens to bump into a helium atom, they actually combine and make a carbon atom. And this carbon atom is stable. It just releases a little bit of energy before becoming stable. So that's how actually carbon is made. We know how helium is made through the proton-proton chain, and now we have this process making carbon. And it's even possible that some carbon can combine with another helium atom to make oxygen atoms. And this is the stuff that we're breathing right now from a star long ago that already died and spread all of its gases everywhere. The oxygen coalesced on Earth, and now we can breathe it, which is insane to think about, that the atoms around us were made somewhere in there. Here's a whole picture of the whole thing. Okay. My GeForce Game Ready driver is available. Great. So what is different about the core of a red giant that allows helium to fuse when it cannot occur in the core of our present-day sun? Right now we're talking about different stars, right? Our sun is not undergoing helium fusion. Why not? It's extremely simple why it's not doing that. Our sun is not hot enough, nor is it pressurized enough to do that. Our sun is not there yet. It'll get there eventually. But right now it is not nearly hot enough for that. And we see here in a red giant, the core is at a significantly higher temperature and density that allows helium atoms to combine and fuse together. Our sun is not there yet. It's only fusing hydrogen. It's not fusing helium yet. So then the question is, well, how do we know once we make that jump, right? How do we know once we're out of the main sequence into being a red giant? Is there a process? Is there like a literal moment, like now you're a red giant? And the answer to that question is it depends. In really big red giants, the fusion of helium kind of begins gradually. So just over time, the core kind of gets hot enough to start doing it, and then it's like this slow, gradual process to where the helium gets to start fusing and the hydrogen fusing at the same time. But with smaller stars, between 0.4 solar masses and 3 solar masses, somewhere between those, we're including our sun, it does not occur gradually. Instead, it has to occur suddenly. And we call that process a helium flash. A helium flash is, we won't be able to see this, but you'll see why it's called a helium flash. It's because it happens so fast. So in a red giant with a mass between about 0.4 masses and 2 to 3 solar masses, the core behaves very differently than the way normal gases behave. Okay? So normally if a gas expands, it cools down. And if it's compressed, it heats up. That's what gas does. And with the star, for example, if the rate of thermonuclear reactions in the star's core increases, the additional energy releases heat, and that expands the core. Okay, but we just said if you expand a gas, it cools down. So this cools the core gases and slows the rate of thermonuclear reactions back to what it was. So um, you increase the thermal reactions, that expands all the gases, which cools everything down, which lowers the thermonuclear reactions. Does that make sense? It's a little feedback loop. If any way you can increase the thermonuclear reactions, we spread the gas out even more, but once the gas gets spread out, it cools down, which lowers the rate of thermonuclear reaction. So it's this feedback loop. But it's possible to break that feedback loop. It is possible to break that feedback loop because you can only squeeze something so hard. There's a limit to how much you can squeeze some things. And in stars, in the core of stars, we approach that limit, and the star is not happy about it. And this is how we get the helium flash. So normally a star acts like we just described. It normally acts like a gas. However, in red giant with a mass between 0.4 and 2 to 3 solar masses, it behaves a lot more differently. In a red giant, the core must be compressed tremendously in order to become hot enough for helium fusion to begin. At these extreme pressures and temperatures, the atoms are stripped of their electrons and become completely ionized. As a result, most of the core consists of atomic nuclei and detached electrons. So it's just a bunch of atoms and electrons floating around in there. Eventually, it keeps getting squeezed so hard that the electrons are right next to each other. They're not even attached to an atom anymore. They're just floating around kind of almost next to each other, but not quite, because they don't really want to be next to each other at all. And eventually, we squeeze them so hard that they literally cannot be squeezed any closer together. And they produce a powerful pressure that resists any further core contractions. They're no longer acting like a gas. They're no longer acting like the rules that we think exist. They're not acting like those anymore. And that's when they become degenerate. And degenerate electron pressure is what's holding some of these things together. Supports a helium-rich core with atom packs so closely as negatively charged electric repulsing electrons will allow. Meaning, it doesn't matter how hard you squeeze after this point, this pressure will keep that core from contracting anymore. You cannot squeeze it anymore with this type of stuff. And in fact, it doesn't even care about all those gas laws anymore. Remember, we said if you heat up a gas, it expands. This degenerate electron matter, it doesn't care. It doesn't listen to what the temperature is doing. The pressure is independent of temperature now. We have heated up so much that temperature doesn't mean anything. We squeezed it so hard that temperature and pressure can't affect what this stuff is doing almost. At this point, you should go ahead and pause the video and watch this video, because this guy explains everything we just talked about, but there's like videos and stuff. So go ahead and open this, pause it, and then come back to this video once you do that. Okay, this is assuming you watched that video. If a core of degenerate electrons actually depended on temperature, how would it respond to an increase in temperature? Well, normal gases expand when temperature increases, which does not occur in a core of degenerate electrons. Okay, so if it did, it would act like a normal gas and expand, but it doesn't, right? Why is the star fueled by a hotter core of helium? Oh, I'm sorry. Why is the star fueled by a hotter core of helium fusion less luminous? Well, the star is less luminous because a hotter core expands, which reduces the temperature of the outer shell, which slows the shell hydrogen fusion reactions, reducing the overall energy output. A lot of like loops and feedback loops, and because of this happening, then this happens, which causes this to happen. Before we move on, I want to explain the term helium flash. We can't see that, like I said before. If we could, it'd be pretty bright, because the amount of energy released by helium flash is actually, it'd be brighter than like a galaxy. But we can't see it for two reasons. First, a lot of the energy that's released actually just goes into heating the core and kind of resetting those degenerate electrons. And secondly, the energy that does escape the core, so if it's not doing those things, it pretty much just gets absorbed by the star's layers, the outer layers. So the light never makes it outside of the star. It just does a bunch of crazy stuff inside of the star. So when an aging star first becomes a red giant, the luminosity increases and the surface temperature drops. The post-main sequence star moves up and to the right along a red giant branch on the HR diagram. So what that looks like is this. We're here, and it goes whoop, like that. It goes and joins the red giant branch. Okay. The luminosity increases and the surface temperature drops. So we can see that here. The surface temperature drops going this way, so it drops. And luminosity increases, so it goes up. So it goes to the right to lower temperature and up to increase luminosity. Once helium fusion begins, though, the core expands and starts to cool down. The hydrogen-fusing shell also cools down, which means the luminosity of the entire star decreases as well. And that's what we see right here. Right? That's what we see right here. But if you'll notice in that picture, there is another figure over there, and that's for the AGB stars. So there's actually a second red giant phase that stars can enter, and these are called asymptotic giant branch stars, or asymptotic, depending on how asymptotic. I've heard it pronounced every single way. Giant branch stars, or AGB stars. And their evolutionary tracks approach the red giant branch from the left on an HR diagram. So we see this star joins the red branch, drops off this way, and then enters a second red giant phase by doing this right here, joining the asymptotic giant branch. Okay. So let's go ahead and go through each of these steps to fill in any more blanks that we might have. So number one says along the red giant branch, the star shines by shell hydrogen fusion. The inert core shrinks and the outer layers expand. All right, so that's what we got going on right here. Shell hydrogen fusion, not core hydrogen fusion. The core is shrinking and the outer layers are expanding. Step two, luminosity increases and surface temperature decreases, so the star moves up and to the right. And we talked about that a second ago. Surface temperature decreases going that way, and luminosity increases going that way. Once we get to this part right here, the core helium fusion begins with the helium flash. And once the helium flash happens, that is when helium starts fusing in the interior. So the star now shines by shell hydrogen fusion and core helium fusion. So both of those are happening. The shell is fusing and the core helium is fusing. So we're getting more helium, but we're also making carbon and oxygen. As it's doing that, though, the core expands and the outer layers shrink. So we go this way. And the star can use helium a lot faster than it can use hydrogen. In fact, this right here only takes a fraction of the time that it would take to burn off all the hydrogen. So just going through fusing helium is a lot faster than fusing hydrogen. So we go down this way, and eventually, a lot quicker than we reached with hydrogen, all of the core helium is used up. So there's no more fuel again. Remember, there was no more hydrogen fuel here. That's why we ended up that way. This made us hot enough to start using helium as a fuel, but eventually we can use up all the helium. Okay? So step 7, the star now shines by shell hydrogen fusion and shell helium fusion. So the interior of the core is no longer doing anything, just the shells are. There's a shell of hydrogen fusing on top of a shell of helium that's fusing, and then the interior of that is just a bunch of carbon and oxygen that's not really doing anything. And that's right here. So luminosity then will increase again, and surface temperature will decrease again. So the star moves up and to the right again. So you'll notice it kind of goes whoop, and then it starts back down, and then it goes whoop. It goes like that again. And eventually the star will shed its outer layers. We'll talk about the planetary nebula in just a second, but that's pretty much the first like 2 stages after a star leaves the main sequence. It goes up here, kicks off helium fusion, runs out of helium fuel, and then starts doing only hydrogen and helium shell fusion instead of core fusion. So our horizontal branch red giant stars becoming more or less luminous. Well, let's go back. Horizontal branch, right? So our horizontal branch red giants becoming more or less luminous. Since they're moving to the left and are increasing their temperature, they're not changing their luminosity. And we see if once they're in this thing, if they're staying horizontally, right? They're staying horizontally, that means they have the same y value, which means they have the same luminosity right there. So here we see the structure of an old, moderately low mass AGB star. So this is the stars that are right here. Okay. They have the carbon and oxygen core not doing anything. They have a shell of helium that's still fusing. And at this point, you see it's a dormant hydrogen fusing shell, but at one point this was also fusing. We see Earth's orbit would be this big. So not Earth itself, Earth's orbit would be as big as this star is, which this star would be gigantic at that time, but that's why they're called giants, right? And remember in 11.3 we were talking about how we can study stellar clusters and find out information about the ages of stars. So what's actually happening here is pretty interesting. So the main sequence would go like this, okay? Something like that. But the only stars that are still in the main sequence are all of these cooler stars down here. Remember we talked about the cooler stars get to stay main sequence longer. So all of these older stars have already left the main sequence. We see here's the turnoff point, which means these stars are currently in the process of heading off to be a red giant for the first time. We see the red giant branch. So all these guys have already turned and gone that way. Some of them have already gone back down here and become horizontal branch stars. And then some have even already started going back up to become the asymptotic giant branch. So in this stellar cluster, we see the life cycle of these stars kind of mapped out. The main sequence ones, we see the turning point, which means in a couple, I don't know, billion years, this turning point will be down here instead. All these stars are heading up to be a red giant for the first time. Then they're going to go back down to a horizontal branch, and then go back up to an AGB star. And then I would suggest finishing off this section by watching this video, because he explains everything we just went over, but everything as in like 11.1 to 11.4 in a matter of, I think, 15 minutes or something. So this is a really good review. I would definitely, you can end this video and then go ahead and open this one. And that's it for 11.4.